Alright, silly people, here's the situation. We are in the finite square well again, and we're just going to kind of go through a really long process to try and get the transmission coefficient that Griffiths got. So this is just running through what Griffiths did between the lines, pretty much. Starting with these two equations here, and we're going to, first of all, solve for C and D in terms of F. So, just looking at the first equation here and solving for C, we have that this is going to be f e to the I k a sine, or actually over sine LA, and then plus, and actually minus d cosine LA over sine LA, right? Um, And what we're going to do is we're going to plug this expression for C into the other equation that we started with. So we have L times F e to the I k a over sine LA times cosine LA minus d cosine squared LA all over sine LA minus d sine LA equals IKF e to the IKA. So I want to combine the expressions that d are attached to. So we have cosine LA over sine LA here, plus d, or I'm going to actually do minus d, cosine squared LA minus sine squared LA, actually plus sine squared LA over sine LA. All I did was collect the terms under the same denominator there. And you see that that numerator is just 1, so we have L f e to the I k a cosine LA over sine LA. And then I'm going to move the stuff which depends on f over here to this side, so it's going to be minus IKF e to the IKA. And then over here we're going to have, and that should be divided by L to make sure it has the same constant. And then on this side is going to be DL times 1 over sine LA. And then we can multiply both sides of the equation by sine LA, and we can cancel out the L's. So we have that f e to the IKA times cosine LA minus IK over L times sine LA equals D. And we're going to take that equation to the bank with us. So let's go ahead and box it. Okay. So next we want to turn back to our expression for C and plug in what we got for D into that. So we have C equals f to the e I k a. We have from the C term just a 1 over sine LA, but then we have the D term in there, so minus, we're multiplying by cosine and dividing by sine. That is pretty crazy. So cosine squared LA over sine LA minus IK over L cosine LA, right? So we can collect these terms again. We have, and actually there is a minus sign on this stuff, so this should be plus here. And then these are already the same denominator, so we'll just collect them like this. Sine LA plus ik over L cosine LA. But then 1 minus cosine squared is just sine squared. So we have f e to the ika sine LA plus ik over L cosine LA. And that is also an equation that we'll take to the bank with us. Griffiths then tells us to plug these two expressions into a couple of equations that he got as boundary conditions. Um, those being that, I'm going to do this next bit in blue, that a e to the minus ika plus b e to the ika equals minus c sine LA plus d cosine LA. And also about a boundary condition ik e to the minus ika plus, or actually this is minus b e to the ika is equal to L times c cosine LA plus d sine LA. Yeah, so that's what we're plugging into. We're gonna plug our definitions to C and D into the first equation that we have here. So a e to the minus ika plus b e to the ika. That is looking like minus c times sine LA. So all these terms are going to be proportional to f e to the ika, but we have minus sine squared LA minus ik over L cosine LA sine LA. And then we have plus d cosine LA, so plus cosine squared LA minus ik over L sine LA cosine LA. So we can collect those terms in a certain way. Cosine squared minus sine squared is just cosine 2LA. And then we have 2 times cosine LA sine LA, which is another trig identity, which is just sine 2LA. Right, and that's what we're getting for this expression, and that's actually how we're going to leave it for now. We can take that to the bank with us. Because it's quite useful that way. It took a long time for that line to straighten out. So next thing, let's do the other boundary condition. So let's write it like a e to the minus ika minus b e to the ika equals L over ik times c cosine LA. So we're going to have all of these are going to be f e to the ika, right? So we have sine LA cosine LA plus ik over L cosine squared LA, and then the other term was d sine LA. So just looking back at what I had for d, it's plus sine LA cosine LA minus ik over L sine squared LA. And then we get the same sort of trigonometric functions in there that sum up in the same way. We have this thing plus this thing makes sine 2LA, and then this thing minus this thing makes ik over L cosine 2LA. And so that's what we're getting for that. And we can bank that. All of this is to get an equation for B in terms of f and an equation of f in terms of a. Right. So what we're going to do is we're going to notice that if you add up, or actually let's do the first term that we calculated, that sum of the b and a terms, and then take minus the difference term, which we also calculated, because that's just going to give you 2b e to the I k a, right? The a bits will cancel out. So let's subtract these terms. We have f e to the I k a. We're going to have cosine 2LA minus IK over L sine 2LA. We're going to have plus, no, we're going to have minus L over IK times sine 2LA, and then minus cosine 2LA. All of that equals 2b to the IKA. The cosine terms do get canceled out, so that's fun. So we have f e to the IKA, and also let's just go ahead and cancel out those exponential terms. Bam, bam. F times sine 2LA, and then there's this really funky term which is minus IK over L minus L over IK, and that's equal to 2b. Let's divide the equation by 2 since we are solving for b after all. And let's also factor out an I over LK from the funky term. So we have sine 2LA all times, and then this is going to be minus k squared plus L squared. And that's b. And yeah, that's what Griffiths got even. So we'll have IF over 2LK sine 2LA times L squared minus K squared. That's pretty cool. The next thing that we're going to do is we're going to see that if we add the two expressions which we calculated, which were a e to the I minus IKA plus b e to the IKA, and then we add the difference term, we just get 2a e to the minus IKA, and the b's cancel out. So we're going to take these two equations here and sort of add them up. So we have f e to the IKA cosine 2LA minus IK over L sine 2LA plus L over IK sine 2LA plus cosine 2LA. And on the right hand side it's 2a e to the minus IKA. Okay, we are solving for f, so let's divide both sides of the equation by an exponential term, and then combine these things here. Minus, and there's going to be a, let's do plus 2 sine 2LA. It'll be L over IK minus IK over L in there, and this on this side it's going to be 2a e to the minus 2 IKA. We'll divide both sides by 2 actually, so we have cosine 2LA. So this is going to be divided by 2. Let's also factor out a minus I over L, okay? And with that, you get a term which looks like L squared plus K squared. Yeah. Pretty cool stuff. And then on the right hand side is now just a e to the minus 2I k a. And then we can put f on one side and the other stuff on the other side to get the same equation that Griffiths got as well. So that's cosine 2LA minus I over LK L squared plus K squared times sine 2LA. Right. So that's pretty awesome. And there should be a 2 here. Yeah, from there. Cool. Now we can get on with actually calculating the transmission coefficient, which, as usual, is defined by f over a mod squared. But Griffiths calculates the inverse transmission coefficient, so let's just do that instead. And if we want to, we can invert it later. A over f mod squared. And from this expression, which we just proved to be true, we can get an expression for a over f. So t minus 1 will be the mod squared of cosine 2LA minus I over 2LK L squared plus K squared sine 2LA. It's going to be the mod squared of that and also times the mod squared of e to the 2IKA, but the mod squared of that is 1, so that's lovely. We'll just do the mod squared then. We're going to have a cosine squared 2LA. The cross terms will get canceled out, so we'll have L squared plus K squared all squared over 4L squared K squared times sine squared 2LA. And then using the fact that we know that sine squared theta plus cosine squared theta equals 1, we can write cosine squared 2LA as 1 minus sine squared 2LA and collect it all into one term. So this is going to be 1 here. And then in brackets, let's have L squared plus K squared all squared over 4L squared K squared minus 1. And this is going to be sine squared 2LA. And now this is just going to be a bit of algebra, actually figuring out what that term is from the definitions of K and L, which Griffiths defines as root 2me over h bar, and then L was the square root of 2me plus v naught all over h bar. Right. So this term is looking like we got, okay, let's do the 1/4 first, and then let's write the inverse of L squared K squared. So it's going to be h bar fourth over 4m squared times, down here it's going to be e times e plus v naught. Right. And then the L squared plus V squared stuff, we're going to have 2me plus V naught over h bar plus h bar squared, haha, plus just 2me over h bar squared, all squared. Okay, I feel like we're really getting somewhere right now. Let's just take off the h bar fourth over 4m squared, because this term, when we square it, we're just going to end up with a 4m squared over h bar fourth as well. And then we're going to have a fraction, which is just e plus v naught all squared plus e squared plus 2e plus v naught, right? And that's going to be over e times e plus v naught. Okay, so we're going to let this big term cancel out this big term. We're going to have 1/4. Expanding that square, we'll have just a total of 4e squared plus 4e v naught plus v naught squared. Yep, and that's all over e squared plus e v naught. And now you see that this term is the identical to this term. It's just multiplied by 4. And I've been neglecting the -1 the whole time, so let's write those on. So this is going to be 4 plus v naught squared, and on the denominator I'm going to recombine it to look like that. So it's going to be e times e plus v naught minus 1. So distributing the 1/4, we'll have a 1 minus 1. So in total, it's v naught squared over 4e plus v naught. And we can plug that into our expression for the inverse transmission coefficient now. So it's 1 plus v naught squared over 4e plus v naught sine squared, and that's actually put the definition of L into the sine squared. It's that. So it's 2a over h bar times square root 2m e plus v naught. And I think that's what Griffiths got as well. So we're all gangster there.